compute average of two numbers many times in our programs. For example, when we do binary search, we do a plus b by 2 or left plus right by 2, something like the middle index we need to compute. So many times we will simply write a plus b by 2, and that may be okay for some set of inputs that we test, but not necessarily okay for all possible a's and b's. So how do we make sure that our program that computes a plus b by 2 is secure, in the sense that the average is a number between a and b, not below a or above b, right? So if I have two numbers that are more than 0, and I want my average to be also be more than 0, right? That's basically what my expectation is. And if my one number is less than 0 and the other number is also less than 0, then I would like the average to be less than 0 also, right? So if you think about it, that may not be the case in computer arithmetic. The reason is that a and b, when we add, because we are working with finite bounded list of numbers, right? It's not like a number line, it's more of a circle. If you search online, for example, go to Stack Overflow, you see a bunch of solutions discussed. And there's always a question of how do we know whether those solutions can be trustable. Sometimes they get high score, but doesn't really mean you can trust them, right? So we need some way to verify the solutions that are discussed over there or trustable solutions. So I will show you that it is possible to verify existing solutions against some kind of a specification, right? So what is the specification for a plus b by 2? That is the first question we need to answer, right? So what I'm going to do is I'm going to use Z3, the SMT solver from Microsoft, and I'm going to specify the behavior of average of two signed numbers a and b, two's complement numbers a and b, more precisely. So what it means is that, say, let's assume we have a magic way of expanding our bit vector size. Okay, suppose a is a number, right, which takes say 8 bits, but we have one more bit. Okay, that means a suddenly becomes 9 bit. Okay. What we will use is so-called sign bit extension technique, right? That should be something that is familiar to you, because we talked about sign extension in my previous sessions. So what is the purpose of sign extension? Say, let's take a simple number. Let's say our number a is just made of 2 bits. Okay, so let's say this number. What is this number? This is -1 in binary, right? When we have 2-bit numbers in 2's complement, this is nothing but -1, okay, in base 10. Okay, so if I now just do a sign bit extension, all I do is I make it to, say, I expand it to one more position to the left, right? That's the meaning of the sign bit. So what is the value of this whole thing in base 2? Is still -1. Okay, so sign bit extension preserves the old value. That's the major thing that we will leverage in this specification. Okay, so we will specify a plus b by 2 using this notion of sign bit extension technique. So what we are going to do is we take a and we apply a magic sign extension function, right? So it will extend our a by 1 bit, right? I'm going to extend it by 1 bit. Okay, say let's assume there is a magic function sign extension which will just extend our number by only 1 bit, right? So 2 bits become 3 bits, 3 bits become 4 bits, and so on. So and then we do the same for b as well. So both a and b are now expanded by 1 bit to the left, right? So the question now is, what can we say about a plus b in this scenario? Well, a plus b can still overflow, but let's reason about what kind of overflow is that. Okay, say let's assume a plus b overflows, right? That what happens in that case? It means that our original, there are two possibilities. Let's say our original a and b are so small that it never overflows. Okay, but still it is possible that the sign extension causes the overflow, because Remember, the most significant bit will have 1 turned on because of, we said, sign extension, right? I'm assuming here both A and B are less than 0, okay, for a moment. So let's consider this scenario. When A is less than 0, B is less than 0, what is the most significant bit? The most significant bit is 1, but because of sign extension, we will be sure that the most significant bits are now 1 and 1, right? Now if we add, right, 1 plus 1 is carry over. Well, let's consider this scenario. 1 plus 1 is 0. And since I said both A and B are also less than 0 originally, that means they must be having a 1 and 1 here, right? And 1 plus 1 is 0. And here is possibly, let's say, we get a carry from this part. So what will happen now here is this will become 1, this will become a 0, and this is going to be a 1, which we can throw away, okay? So we throw away this particular portion of the answer. So what it means is that we still preserve the old sum, right? Because we have the old values are in this part, right? Just to be clear, right? This is the old value of A and B. We did a sign extension, have extra 1 bit, stick to the most significant bit, and we are sure that 1 plus 1 is, when you add in binary, it will be 1 0, right? And that's the one that will be discarded, this one, right? And if we get a carry during the overflow, let's think about that problem for a moment. Meaning we will have some extra bit coming, right? And that bit will take this position and have a 1 here, okay? Suppose there is no carry. That means when you add A plus B perfectly, we will not get any carry. So in that case, we will have a 0 here, right? Because 1 plus 1, as I said, is 1 0 in binary. So we'll have 0 here. And in the end, we can discard this as well, right? Because it's 0 in the beginning. So the 2 scenarios, just to clear up. One is we do sign extension, and because of sign extension, we can be confident that we have a room for carrying the carry bit, okay? So the carry bit will be taken to the most significant bit. And then we can do divide by 2. So when we do divide by 2, then what will happen is the number of bits will reduce by 1. That's the meaning of divide by 2. So our answer will be perfectly fitting in the original area, right? The original list of bits that we are assigned at the beginning, okay, before the sign extension. So that's the core idea of this specification. So all I'm going to do is take my A, extend it by 1 position, take my B, extend it by 1 position, and then I say the answer is just A plus B by 2, right? But now you have to truncate the most significant bit because we have added an extra bit, right? Because of the sign extension. After we do the A plus B by 2, we truncate the most significant bit, meaning we will only select the number of bits we were originally given. Okay, that's the idea of the specification. I will make it more precise when I show the code, but this is the general idea. Why would that work? That works because I said based on the reasoning that I gave it to you, we create room for the carry bit, right? And therefore there is no overflow. And then we divide it by 2. That means we will be able to go back to the original size. That's basically the idea. Okay, given that background, now let's take a look at different implementations that might come online if you search on the Stack Overflow site that I will point you to. And I'm going to pick a few implementations from there and verify it against the specification that just I outlined. Okay, so now I'm going to show my implementations. So what I'm going to do is now I'm going to show to you, right, one moment, my Z3 implementations of that specification problem. Okay, so first is the specification. Let's focus on the specification, right? What did we say about the specification? We said we are going to do sign extension, right? From Z3, right? We can easily specify this. Take the number A, sign extend by 1 position, take the number B, sign extend by 1 position, and then compute the average. That's the average that you see, T by 2 is the average. And then we will extract only the necessary bits, meaning we will throw away the most significant bit because we just did a sign extension. That's basically the extract function. It's part of Z3. Okay, so we'll start from the 0th position and all the way go to the W minus 1th position, extract the those bits from the answer T by 2, which is the average. So this is the specification. Okay, this specification will be compared against multiple implementations. Remember, in C language, you can't extend by one position, right? If you have a 32-bit integer, you cannot ask for a 33-bit integer. You have to either go through long or or whatever you have. So let's consider now different C implementations that you can see online. If you go to the, for example, the Stack Overflow site here, take the average of 2 signed numbers in C, and they give you a bunch of implementations. So I'm going to take two of those, and then I will use the binary search one, 3 implementations, and compare against the specification. Okay. So what is the first one I saw? The first one I saw was this, right? Let me go to this particular website. Maybe it's easier. So what I'm going to show to you is basically the first implementation from this site. Okay, so what you're seeing now is the average of 2 signed numbers solution, right? One solution that somebody's talking about is A by 2 plus B by 2, and some tricks with the percentage and whatnot, modulus or reminder or whatnot. So I'm going to take this example. So here is one code that say, okay, so they say if A is less than 0 is true and B less than 0 is also true, that means they both are same sign. Or if A is 0 and B is greater than 0, then they will also be same sign. In that case, they do this computation, otherwise they do this computation. So now we can just take this, encode it in Z3 and compare against the spec that I have explained to you. That's what I'm going to do for you now. And then I went down further, and I saw some more implementations, right? There was another implementation from someone who said that, okay, here is another implementation that I will be using. This is coming straight from binary search idea, right? Many implementations of binary search has this idea that, okay, instead of A plus B by 2, you would compute B plus A minus B by 2, which seems to be reasonably okay, but it's not quite correct. I will show you why it's not correct also. Okay, and then I saw somebody else referring to the Hacker's Delight book, and they mentioned this portion of code, but they didn't show. He claims that, well, it's probably true, but he claims that he checked it using Z3 solver, but he didn't put the Z3 code as far as I know. So I'm developing my own Z3 spec for this, right? Okay, so we will be taking these 3 implementations and compare against the spec. Okay, that's basically what I'm going to do now next. All right, so we have the spec, which is this nice spec, very simple and compact. And now we are going to do the first implementation. We said, now, by the way, you have to notice that I translate the C code into Z3, right? You could directly run something like Z3 if you install CLI, which is a symbolic execution kind of technology. But I am directly encoding it in Z3, Python API. So this is the first implementation. It said, if both the numbers are negative or positive, both are positive, that's what I encoded here, then what are we going to do? Then we know they are same sign, right? If they are the same sign, the first solution is A by 2 plus B by 2 plus A mod 2 plus B mod 2 by 2, okay? That's basically what they said. Otherwise, they do the regular A plus B by 2, right? If the signs are opposite, then there is no problem with overflow. A plus B will not overflow if they are opposite. Okay, so that's basically the first implementation. The second, more compact implementation coming from the Hacker's Delight book was this one. Okay, it uses bitwise and bitwise exclusive OR and right shift, and also it does some logical right shift. In Z3, there is LSHR to do logical right shift. So that's basically the second implementation. And then the third implementation, which is very buggy actually, is A plus B minus A by 2, which is the one that you see in binary search code. But in binary search code, there is some more property associated with the A and B. It's not just for all A and B, you can't do this, okay? All right, let's start now verifying using Z3. We claim now our spec is not equal to the first implementation. Let's see whether that is true, okay? If that is true, Z3 will come up with an example. If it is not true, Z3 will say, I'm unable to satisfy this expression. That means this expression spec must be equal to the implementation, right? That's something we have talked about earlier. So let's give it a try and see what happens now clearly. Python, yes, average is my implementation verification. So it's going to verify the spec against the implementation. So it says spec equal to implementation, perfect. So let's move on to the second implementation now. We verified against the first, very good. Let's do the second. Okay, it also works. But now let's look at the third one, which is extremely simple, the binary search kind of thing, right? People use all the time in binary search like this. Why? You will be surprised that this particular implementation is not quite right. Okay, it's wrong because it was able to come up with an example. It says, if you plug in this A and this B, the specification says -26 blah blah, and implementation says 1879. So either the spec is wrong or the implementation is wrong, but I shown to you that the spec is correct based on the mathematics. We proved it, as therefore the implementation is wrong in this case. We also checked the same spec against other two implementations, right? So why is this implementation wrong? It's wrong because it assumes that doing a plus b minus a by 2 is same as a plus b by 2, okay? Which is mathematically true, but not in a computer arithmetic. So we need to add more constraints to make this happen. Let's say I add another constraint saying that, as in binary search, your left is smaller than right? And both A and B are positive. In your binary search, the indices are positive. So if you add that, then even in the binary search algorithm is correct in terms of how you compute the midpoint, okay? So, and always A is less than or equal to B, right? We can even add this. Okay, let's give it a try and see what happens now. Hopefully it shows the spec is equal to implementation. As you see that I have simply, of course, it takes time to come up with this little specification. Once you have a spec, now you can compare against different C style of implementations, right? By directly encoding it in Z3. Z3 has lots of bitwise operators and other functions built in for us. Only this first implementation was a bit involved for me. And I also learned that when the bit vector size of A or B is just 2, which is not possible in C. In C, the minimum size is 8 bits as far as I know. There are some challenges when you directly put it in C3, but that's not important for this talk. Other than that, I was able to verify mechanically, as I've shown you, and proved that the specification is equal to implementation, okay? And we are able to successfully compute the average of two numbers without problems, without overflow problems. Thank you very much, that's all.